Testing 1, 2, 3, testing 1, 2, 3. Hello and welcome back to Math Class in Session. Today, vectors in R cross R and R cross R cross R, sometimes known as 2-space and 3-space, where 2-space is our familiar Cartesian plane. R stands for real numbers, and R cross R means two real number lines meeting at the origin. Vectors in R cross R, the Cartesian plane. Each point P in the Cartesian plane uniquely defines something called a position vector, where O is the origin, the vector OP. For example, the point P, 2, 3, uniquely defines the position vector 2, 3. This is how. Here's our point 2, 3, and when we go from the origin to that point, there's a unique vector associated with that point. Every point has a unique vector associated with it. And 2, 3 could refer to the point, or it could refer to the position vector, depending on the context of the discussion. Vectors have components instead of coordinates. Points have coordinates, vectors have components. Algebraic vectors are ones you'll find on a grid, like the one in front of you, as opposed to geometric vectors, which aren't associated with a grid. They're off the grid, like in, say, physics class. In diagrams, you'll find directed line segments that are vectors, but they don't have a grid associated with them. Vectors in R cross R cross R. Well, it's the same idea. It's just that now we've got three coordinates. Now, if you were this guy looking into a room where this is the front left corner of the room, front left bottom corner of the room, kind of looks like the corner of a room, and from his eyes, he is looking at the X, Y grid. The Cartesian axis is the floor, while Z is this new coordinate axis that just protrudes straight up out of the floor. So that's how it's set up. And points in this 3 space are arranged X, Y, Z. They just got 3 coordinates. We'll start off by plotting a point in 3 space. Let's plot the point 3, 2, 5, where it's X, Y, Z. So X is 3, so we measure 3 along the X-axis, and I guess we could call that point A. And since Y is 2, we'll measure 2 along the Y-axis, and so we'll call that point B. And we'll measure 5 along the Z-axis. So straight up there, we'll call that point C, 5. This is how we start to plot a point in 3 space. Now the next little trick is you have to create parallelograms. So every single line we draw, every single line I draw from here on out is going to be parallel to one of these axes. That, for example, is a parallelogram, where this side is parallel to the y-axis and this side is parallel to the x-axis, and I've made a parallelogram happen. There, I've done it again. This side is parallel to the z-axis, and this side is parallel to the x-axis, and it forms this parallelogram. And you'll notice the length of this side is 5. Here's another parallelogram, which happens to be a rectangle. This side is parallel to the y-axis, and this side is parallel to the z-axis. And finally, I drew one more parallelogram, where this side is parallel to the y-axis, and this side is parallel to the x-axis. And to complete this box, if I joined this point with this point, I would have completed a box built out of parallelograms. And now we can see the point in 3 space. So we could label it point 3, 2, 5 and draw the position vector associated with it in 3 space. That's an intro to vectors in 3 space. Now, Let's have some fun and state coordinates of some of these points. I see A, B, C, D, E, F, lots of points. Let's state their coordinates. The coordinates of A. Well, we went, since this is 3, 2, 5, we went 3 along the x and nowhere else. So 3, 0, 0. The coordinates of B. Well, we went 2 along the y-axis and nowhere else. So therefore, it must be 0, 2, 0. The coordinates of point C. Well, we went 5 along the z-axis and nowhere else, because we're still on the z-axis. So it must be 0, 0, 5. A, B, C. That's point. How about point D? Well, we went 2 along the three along the x-axis and 5 along the z-axis. So it must be 3, 0, 5. E. Point E is located here. How did we get there? We went 3 along the x-axis, 2 along the y-axis, and nowhere along the z-axis. So it must be 3, 2, 0. F. Point F. How did we get there? We went nowhere along the x-axis. We just went 2 along the y and 5 along the z. So it must be 0, 2, 5. And gradually, by dwelling on this and practicing with it a bit, you get used to points with coordinates in 3 space. Well, since this comes with practice, let's go again. Plot a point and draw the vector. And the point's got some negative signs in it. Okay, there's our coordinate grid system. Let's measure -2 along the x-axis. So this is going to have to extend back, -2. 4 along the y-axis. Okay, so there it is, 4. And -3 along the z. So there's z. We'll have to go down because it's -3. So there they are. And now you start drawing lines that are parallel to the axes and making those parallelograms. You can't miss. I mean, if you're just drawing lines parallel to the axes, you have to get there. So I made a parallelogram here. I just drew parallel to the y-axis from this point and drew parallel to the x-axis from this point, and there's a point there that forms a parallelogram. Again, I just drew parallel to the z-axis and drew some more parallel to the x-axis, and it comes to this point T. Next, I went parallel to the y-axis and then parallel to the z-axis, and it forms this parallelogram. Finally, there's one point missing, and it's over here somewhere. So let's see if we can find it. Okay, I went straight down from S because it's got to be parallel to one of the axes. So I went parallel to the z-axis, and from here I drew parallel to the y-axis. And now there's just 2 points to close up, and we have formed that rectangular prism. And so the vector goes from the origin through the rectangular prism to the other corner. And there it is, the vector -2, 4, -3. It takes a little practice to draw points in 3 space. Naming a few of these just for fun. Let's see. We got P, Q, R, S, T, U, V. P, well, P is I went -2 along the x and then nowhere else. -2, 0, 0. Q, I went 4 along the y and nowhere else, so 0, 4, 0. R, I went -3 along z and nowhere else, so 0, 0, -3. S, how did I get here? I went -2 along x and I went 4 along y, so -2, 4, and nowhere else, so -2, 4, 0. T, how did I get here? -2 along x, -3 along z, but nowhere along y. So -2, 0, -3. U, where is he? There it is. So I didn't go anywhere along x, but I did go 4 along y and -3 along z. So 0, 4, -3. think that covers them all. V, no V. Well, V we know, the coordinates of V is -2, 4, -3. Okay, we've looked at points in 3 space. Let's look at planes in 3 space. I mean, everything's there, circles and lines and things, but right now we've looked at points. How about planes? Consider the plane XY, the XY plane. That's the floor of the classroom. And as long as we didn't go up Z at all, then we're on the floor. There's a picture of it. We used little parallelograms to represent these planes. It extends infinitely in all directions, though. And so as long as Z is 0, we're on this surface. So Z equals 0 is the equation of it. How about the plane, the XZ plane? The XZ plane is this wall. There's a picture of it. And so as long as y equals 0, we're on that plane. So the equation of that plane is y equals 0. And there's one more to discuss here. The YZ plane. Well, YZ, it must be the front of the room right here. Here's a picture of the plane. It's a rectangle, but it's also a parallelogram that extends infinitely in all directions. So that's just the surface of the plane. And as long as x equals 0, we're on that plane. Back to this diagram. The equation of the plane that contains PSVT. Well, here's PSVT. This plane here. Well, it looks like the front of the room just got pushed back. I mean, if you consider the front of the room as a plane that extends infinitely in all directions and pushed it back along this x-axis, -2 units, you'd find that it unites with that shaded plane. So x must equal -2 there. The equation of the plane containing OPTR, okay, this plane, that one. Well, it looks to me like it's the side wall. It's the side wall of this classroom. Sometimes there's windows in it. And so the thing is, it's just the equation of that. As long as y equals 0, we're on that plane. Okay, how about the plane that contains QSVU? Where's that? QSVU. Okay, that plane. It looks like it's the side wall that just got pulled out. It got pulled out along this y-axis, 4 units. So y must equal 4 all over that plane. Because it's parallel to this wall, which is y equals 0, but it's y equals 0 pulled over, so y equals 4. Next, the equation of the plane containing RTVU. RTVU. Okay, that plane. What's that equation? Well, it's the floor, which is z equals 0, pushed down. So z must equal -3. The equation of the plane that contains OQUR. OQUR. Well, that would be that plane. And we can see that that's just the front wall of the room. So in other words, x must equal 0 on this entire plane, which extends up, out, to the left, to the right, downwards, in all directions. As long as x equals 0, we're on that plane.